So let's talk about the following. Let's do this instead. So I want to find the area of the region bounded by y equal to x cubed, y equal to 0, and x equal to 4. And typically, when I'm asking myself a question like this, I usually like to draw the region. It's not an absolute requirement, but it is usually a good idea too. I'm not going to draw it perfectly. That is a 4. Yes, I know. Believe it or not. It's a 4. All right. So I just need a general idea of what this looks like. X cubed, it looks something kind of like this. I don't really care about what's happening over here on the left side of the y-axis because I'm only going from, well, I'm only doing this. Like that. And then I'm stopping at x equal to 4. Nope, can I get that? And I'm also got y equal to 0. So when someone describes a region, the boundaries of that region should fully describe it. Yeah. Some of the Alvarado homework questions, I feel like the way he's describing the region is a little bit dicey, but we'll get around that. So if I want to find the area of this region, I'm going to be adding up all the rectangles. And this is, I especially want to be emphatic here. The reason we're talking about this rectangle idea is because it becomes a lot more useful when we start talking about volumes of revolution, like we're about to. So I'm thinking about taking this rectangle that lives x away from the origin, or specifically from the y-axis, and that area of that rectangle is equal to the height times the base. Or in other words, the height of that rectangle is the top function minus the bottom function. And the base of that rectangle is a small change in x, which you will almost always hear me say is dx. That's the area of one rectangle, and we're doing all the rectangles because we want to find all the area. So we get the total area by adding up all the rectangles from as far left as x equals 0 and as far right as x equals 4. That's how we find the area. Not too surprising. And then we could do it. We would end up getting x to the 4th divided by 4 from 0 to 4, which is 4 to the 4th divided by 4 minus 0 to the 4th divided by 4. You shouldn't calculate 4 to the 4th here. You should calculate 4 to the 4th divided by 4 is 4 to the 3rd, which is 64. Okay. Now, what I want to do is take that region, this region here, and I want to find the volume that I get if I revolve that region around the x-axis. So now we're going to say I want to, so I can try, I'm trying to be better about numbering things. It's probably not going to last, but try. So now we want to find the volume of the solid, writing these out always is a lot of words, obtained by revolving the region bounded by y equals x to the 3rd, y equals 0, and x equals 4 around the x-axis. And I'm going to draw the same first picture. I'm going to draw that area again with my vertical strip. I would like a different pen. There we go. Cool. So here's my same XY coordinate system. I'm not going to draw like all the extra bits here. I'm just going to draw the region and none of like the extensions of any of the graphs. So here's my x equals 4. Here's my y equals x cubed. Meeting up with it. This point here is 4 comma something. Point here is 0 comma 0. And here's our y equals x cubed. And here's x equals 4. All right, and now the idea of taking this vertical strip, what's going to happen is we're going to now revolve this thing around the x-axis. You don't have to draw this next picture. In fact, normally if I was doing this sort of question as a student, I would probably not draw this next picture. But the next picture that we're going to get, if you wanted to draw it, the way I would recommend drawing it is by kind of taking your shape here and drawing it again, and then drawing the reflection of that across the x-axis. So I'm just going to draw the same thing, but down here. And I'm imagining this revolving around and creating some sort of weird looking shape. Specifically though, this little thin rectangle, if you revolve it around 360 degrees, it's going to look like a disc. You're going to get some shape that looks like this. I know how to find the volume of a really flat cylinder. That's what that is. It's a really flat cylinder. So I'm going to say that the volume of this disc, well, the volume of any sort of disc is the area of the circle times the thickness. So it's going to be area of the circle times the width of the slice of the disc. Or better said, that's going to be pi times some radius squared times, in this case, dx, which is the thickness or the width. And then finally, the radius of this circle here, well, it varies, right? For this strip here, it's something, but if I drew like a different strip further to the left, my disc would be a lot smaller. It'd have a lot less volume. So the radius depends on the value of x, and I should say the radius depends on the function that we're using to get the height of our strip. So our radius here is just this. That's our radius, which is literally just the function. In this case, the radius is x cubed. It's how far away the function is from the axis of rotation. If x is 1, the radius is 1. If x is 2, the radius is 8. If x is 3, the radius is 27. As x goes from 0 to 4, the radius goes from 0 to 4 cubed. Questions about this? See faces that look like they have questions. Maybe you don't know, but you might not. We'll continue on. You might not know what your question is yet, which is totally fine. So that's the volume of one slice or one disc. And now, just like when we found the area, we added up all the areas of the rectangles to find the total volume. We're going to add up all the volumes of the discs. So the total volume is going to be the integral from 0 to 4 of pi times my radius. I should have filled in my radius here. My radius was x cubed. So it's going to be the integral from 0 to 4 of pi times x cubed squared dx. Sorry, you can't see that. Apologies. The calculation here is not particularly terrible. We're going to be, I would pull the pi out in front. Get the integral from 0 to 4 of x cubed squared is x to the 6th. We anti-differentiate. We get pi times x to the 7th over 7 from 0 to 4. We plug in and we get some grotesque number, pi times 4 to the 7th all over 7 minus 0. Whatever that happens to be, it's gross. Yeah, it's too big. This is the general process for finding the volume of revolution using what's called the disk method. If you rotate this function around, you're just adding up all the areas of these disks. Now, what happens instead? Yeah, we should go ahead and do this. Yeah, we'll come back to this one. Let's look at the question.
So was the 64 from the previous?
Right, the 64 doesn't really have much to do with this particular problem. The 64 was just the area of that region, which is not really related to the volume at all. But I wanted to talk about the area because I wanted to point out the idea of drawing this strip is super useful. Fun fact, important fact, whenever you're doing a volume like this using either the disk or we'll soon talk about the washer method, the strip you draw, and you should always draw a strip in your region, should always be perpendicular to your axis of rotation. Always. Vertical. Right.
The y-axis, I'm gonna say
right. Yes, exactly. So if you're to rotate around the y-axis, your strip would be horizontal, which would mean you'd have to do the integral in terms of y, not in terms of x. Let's go ahead and do that. Let's actually use the same shape to do that. So now we're going to take the same region. I can number things. So let's just say same region. Now we're revolving around the x-axis. Around the y-axis. Geez, I did it too. Sorry. So here's our good old region here. X equals 4. Y equals x cubed. Y equals 0. You don't need to write y equals 0. And now we're going to revolve this around the y-axis. So just as I said just now, my strip has to be perpendicular to the axis of rotation. So my strip has to be a horizontal strip here. And when I rotate that strip around the axis of rotation, I'm going to be missing some stuff in the middle. Right? There's a whole middle part I'm not going to get. So if I drop this down here, and I kind of just repeat this here. Over here. I have kind of, yeah, I like doing it this way. Here's my weird looking shape. It kind of looks like you took a block of wood, like a log, and you like scooped out a bowl from it. That's the solid we have left. So you took a block of wood and scooped out some sort of kind of parabolic looking bowl from the middle. But the point here is that when I revolve this strip around, well, look what happens. I get this shape here. Whoops, can I get the shape there? Maybe. This is why I don't usually draw this picture in this shape here. What you have is a disk less another disk, better called a washer. It's a washer. You've got some area minus the area we're missing in the middle. So the volume of this washer is going to be, here's how I think of it. It's the big circle area, pi times big R squared, minus the little circle area, pi times little r squared, times the thickness of the washer, which is dy this time, because it's a change in y, not a change in x. Should I turn off a light? Would that be better? Okay. But I just want to point out, right? So I'll point out that right here, there is my small radius, the inner radius, the radius, the distance from the axis of rotation to the function that's closer to it. And over here, there is my large radius, the distance from the axis of rotation to the function that's further away from it.
Sorry.
Go ahead.
That's capital R.
Correct. I'm really just using it to say the volume of this washer. In fact, let me draw my picture one more time because this, I don't love this in here. So this washer can I draw it? So here's my axis of rotation right there. This distance here is the smaller radius.
Oh, the smaller.
Right, I'm just using a little r to be for the small radius and a capital R for the larger radius. And if you take the area of the big circle and subtract the area of the middle circle that's missing, we get the area times the thickness to be the volume of the washer that we have. Yes. Right, the disk method is a special case of the washer method. The special case being that the inner radius is 0. So right, the washer method is the more general method. Yeah. Another way you can tell if you need the disk versus the washer method, which again, like you said, are really the same method, is that for the disk method, the region that you're rotating is flush with the axis of rotation. Or another way you could say it, the axis of rotation is one of the boundaries. Here, the x-axis, which is the line y = 0, is one of the boundaries. On the other hand, the washer method here, the region is not flush with the axis of rotation. There is some separation between our region and the axis of rotation. Or the axis of rotation is not one of the boundaries of our region. Okay, so just like before, we're trying to quote unquote add up all the volumes. Oh, I should probably write down what my I got one step ahead of myself here. Let's actually find what the radii are. So everyone could probably look at this and tell me that the radius of the larger function or the further away function is how far away from the axis of rotation. What number am I looking for? I just said it. It's 4. Right? This straight line here is always 4 away from the axis of rotation. So my outer radius is 4 squared. Well, it says 4. It's 4. And then we square it because it's 4 squared. The inner radius is a little dicier. The inner radius is the function that's closer to the axis of rotation. But we have to change it. We can't write that as y = x cubed. We have to say, oh, instead of y = x cubed, we need x equal to the cube root of y. Because we have to write x as a function of y. Because our integral is going to be in terms of y. So we're going to get the cube root of y, or I probably prefer to write that as y to the 1/3 squared. All times dy. And then to find the total volume, we add up all the washers. So our total volume over here is going to equal the integral from not 0 to 4. We're not going from left x = 0 to right x = 4. We're going from bottom y = 0 to top. Well, if I plug in 4 for x there, y is going to be 64. So when I think about drawing this picture and finding limits of integration, if I have drawn a vertical strip, I think about how far left or right that strip can slide. I can move it as far left as 0, as far right as x = 4. If I have drawn a horizontal strip, I think about how far up and down that strip can slide. As far down as 0, as far up as 64. And then, excuse me, most people, when they do this, they factor out the pi and they just put it in front of the integral. I'm going to say I've got pi times the integral from 0 to 64 of 4 squared minus y to the 1/3 squared. And then the work is going to be kind of gross. It's going to be 16 minus y to the 2/3 dy. Integrating the antiderivative of 16 is 16y. The antiderivative of y to the 2/3 is y to the 5/3 divided by 5/3 is times 3/5. This is the reason, this is one of the reasons why people say something like, set up, but do not evaluate the integral for the volume of such and such thing, because the actual integral ends up being just gross. But if we were trying to do this and actually evaluate it and not do all the terrible work, at this point we would just plug in and leave it. So I would say we get pi times 16 times 64 minus 3/5 times 64 to the 5/3 power. Minus 0. You could simplify this. It does get nicer, but that's not really the point. 64 to the 5/3 power is 1024. You could probably simplify this to some degree. But again, it's not really the point. Questions so far? So I would emphasize it is really, I don't want to say absolutely necessary, but it's pretty close to being necessary that when you're finding these volumes of revolution, you draw the region. You don't have to draw the volume revolved around, but you kind of have to draw the area so you can kind of see how you're going to set up the integral. You don't have to, but it's really, in my opinion, the easiest way to deal with things. Question?
Never mind.
Okay, cool. So let's look at another one. Okay. Maybe if I can turn the page here. Yeah, am I numbering things still? Yeah, I am. Okay, number 4. Let's set up. Oh, yeah. So here's a question that I've seen teachers ask before in the most annoying way possible. No, I think about it. This is not annoying. No, I think about it. Oh, yeah, you can't really ask that question in this class. Never mind. Set up an integral for the volume of the solid formed when the region bounded by y equals x squared, x equals 0, and y equals x plus 2 in the first quadrant is revolved around the x-axis. So I want you all, as quickly as you can, try to draw these 3 graphs on an XY coordinate system, because that's your first step. Draw y equals x squared, draw y equals x plus 2, draw x equals 0. Don't draw x equals 0, it's just the y-axis. I'll give you a minute. Hey, everybody. The graphs are not too terrible. One of them is your regular parabola, one of them is a straight line. I say I give you a minute, 10 more seconds. All right, here's my parabola. If I was being smart about this, I probably would find where these things intersect before I actually drew them, but I'm not gonna. I know y equals x plus 2, I'm just shifting up 2. So it's gonna look like, let's draw it in a different color. It's gonna look like this. And this is where it's easy to make a silly mistake. You're good. It's not all of this, because we also have x equals 0, aka the y-axis. So really the region I'm looking at is this region here. It's bounded by y equals x plus 2, y equals x squared, and x equals 0. And the way we know it's not this region over here is they said it was in the first quadrant. If they said it was in the second quadrant, then we would have this region over here instead of this region over here. Okay, so now I'm going to revolve around the x-axis. So I'm going to draw my strip as a vertical strip. because our strip is always perpendicular to the axis of rotation. And again, I don't really want to draw the volume because I'm not good at it, and you don't need to. But I do like to think about what happens when I revolve the strip around the axis of rotation. Well, let me ask you, is the bottom or the top of the strip touching the axis of rotation? Yes or no? Here's my axis of rotation right there. Is that a strip I just drew touching it? Definitely not. That means we have the washer method. We're going to be missing an inner circle. If the strip was touching the axis of rotation, we would have the disk method, which again are the same, but it still feels like it might be different in our mind. So here's what my shape's going to look like. Or I should say my disk. There's my disk with an inner radius of the closer function to the axis and an outer radius of the further away function. Cool. So here my outer radius is going to be x plus 2. My inner radius is going to be x squared. Which is another reason why it's good to draw the picture so that it's easier to see which function is the one that's the one closer to the axis of rotation and which one's the one that's further away. Because if you didn't draw it, you might just kind of think x squared was the bigger thing because it is the bigger polynomial eventually. But in our region here, it is definitely not the bigger thing. So I'm always a fan of saying the volume of my disk, sorry, it's not a disk, it's a washer. The volume of my washer is pi times my big radius squared minus pi times my little radius squared, all times the thickness, which is dx. I just like to start there. I think it's always a good reminder of what I'm actually doing. And then I can write some more things. I can say, okay, well, that's going to be, if I factor out the pi, my big radius is x plus 2 my squared, and my little radius is x squared, which I'm also going to square. And now I can set up the actual integral for the total volume. So the total volume is going to be the integral, I should put the pi out in front, of x plus 2 squared minus x squared squared. I kind of do like to leave it as x squared squared if I'm not actually going to do the integral, which technically I'm not going to do it because it said set up, right? Someone said set up an integral. They didn't say do the integral. So if this was a test question, don't waste your time doing the integral. What am I missing that I absolutely need to actually write the integral? I'm missing those things, those limits of integration. We can certainly see from our picture that the left limit of integration is going to be 0 because that's as far left as this thing can go. But the right limit of integration is wherever these two things intersect. You can either find that by setting the two functions equal to each other and then doing like math, factoring some stuff, and getting x equal to 2 or x equal to -1, but the -1 is over here, which you don't need. And the 2 is over here, which you do need. Or you could do the easier thing and just guess. If you're trying to find where x squared equals x plus 2, I think we could all look at it and be like, well, if x is 1, that's not going to work. But if x is 2, 2 squared is 4, and 2 plus 2 is 4. If it seems like there might be an easy number that's the right answer, it's okay to just guess it and not actually do the work of solving the equation. So our right-hand limit of integration is going to be 2. And this is how you would set up the integral for the volume of that shape. Do we want to ask the more annoying question? Yeah.
What are big R and like how you define x squared, x plus 2? How did you come to that? Well, I can see how the big R would be x plus 2, and my logic is that it's touching the function x plus 2. I'm having a hard time visualizing that for x squared, I guess. Or I guess because the bottom functions or the bottom of the rectangle is touching the product. That's it. Okay.
Yeah. Another way you can, other words you could say instead are when I draw my strip here, the x squared function is closer to the axis of rotation. So it's the smaller radius, whereas the x plus 2 function is the one that's further away, so it's larger radius. Good question, James. Sometimes people talk about different axes of rotation other than the x-axis or the y-axis. I feel like that's not typical for this class though, so I don't know if we should really waste our time. Well, let me give you one example and then we will not talk about that unless it comes up again. So let me show you. What if instead I wanted to find the same region, but now we're going to revolve it around a different axis, not the y-axis yet, although we are going to do the y-axis. So same region, but now we're going to revolve it around the line y equal to 4. Let's draw the region again. I always think it is worth your time. I almost always think it is worth your time to draw the region. There could be an instance where that's not true. Am I giving myself enough room here? Maybe. Yeah, probably. Okay. Cool. There's my region. There's my y equals x squared. There's my 0.2, 4. There's my line y equals x plus 2. I will mention, if you happen to have a region revolving around the line and the line is cutting through the region, like if I said revolve this region around the line like y equals 3, it's usually problematic. It's usually because someone made a mistake and wasn't paying attention to the question they're asking. It's not usually a question we ask. So if you see that happening, 1, check to make sure you've drawn the region correctly. 2, if it's still the case that your line of rotation is cutting through the region, ask your teacher or the person who had the problem what they meant, because they probably just made a mistake and weren't paying attention. But here, our axis of rotation is not cutting through the region. It's actually just barely right there. So there's our line y equals 4. So if we're going to rotate around that line, so now my little vertical strip, still vertical because it still have to be perpendicular to the axis of rotation, is going to rotate this way here. So something that looks like this. There's my washer. Watch this next part. Here is my inner radius. Literally just the distance from the axis of rotation to the closer function. Here is my outer radius. The distance from the axis of rotation to the further away function. It's always smaller one's the closer one, bigger one's the further away one. Notice though, that compared to the previous problem, the function that is playing the role of the outer radius or the further away function has changed. Now the x squared is further away from the axis and the y equals x plus 2 is closer. All right, so volume of my washer, as usual, let's factor out the pi. It's pi times big R squared minus little r squared times the good old dx. Okay, my outer radius here is not just x squared. In fact, let me be super clear. Over here, my inner radius wasn't really just x squared. My inner radius was x squared minus 0. The difference between my function and the axis of rotation. And my outer radius was x plus 2 minus 0. The same logic applies here. My outer radius is the difference between the axis of rotation and the further away function. 4 minus x squared. And it does need to be 4. Okay, technically you get away with subtracting in the wrong order here because we're going to square it, and if it was negative, it'll turn into positive. But to be correct, we should subtract in the correct order. Y equals 4 is definitely bigger than y equals x squared on this interval, and we should have the bigger thing minus the smaller thing so that our radius is positive. In a similar way, The smaller radius is the axis of rotation minus the closer thing, which is the x plus 2. And now if we want to set up and not evaluate the integral, we definitely don't want to evaluate this integral. It's going to be terrible. The volume is going to be the integral still from 0 to 2, right? That didn't change from last time, right? It was from 0 to 2 last time. Yeah, it was. Okay, good. Still throwing the pi out in front. But then our big radius squared is going to be 4 minus x squared squared. And our little radius squared is going to be 4 minus x plus 2, which, yes, you could simplify as 2 minus x squared. Which is not like, mentally, it's not that hard to do this, right? Like, it's not like a really hard integral to do, but the mechanics of just multiplying it all out and making sure you're keeping track of everything appropriately can get a little bit dicey. It's easy to make a mistake when you multiply this out and get a missed sign or adding something up wrong. So that is often, again, why we say, don't calculate this, just set it up. That's the setup. I don't expect that you all will actually have integrals, volume integrals revolved around other axes other than the x-axis or the y-axis, but I could be wrong. They definitely show up in other classes. Your teacher might be more of a 21B mindset and be like, oh yeah, we can do this other thing, it's fine. So if they are doing ones like this where you're revolving around y equals 4 or x equals 3 or some other line that's not the x-axis or the y-axis, let me know, we'll do a few more. Questions about what we've done here? Okay. Yeah, let's do one. Oh, there's another terrible thing too. Okay, we'll do one more here, and then I will ask you about the terrible thing, and we'll hopefully not have to talk about it if it's terrible. So, okay, one more. Same region again. I know it's boring. Same region, but now we're going to go around the y-axis. Okay, which is going to be really kind of awful. I know. And I had to really sell it, right? It's going to be so fun. No, it's not. It's going to be terrible. I mean, terrible is all in the eye of the beholder. There is my region once again. Here's my y equals x plus 2. Here's my y equals x squared. And now if I'm revolving around the y-axis, I need to use what kind of strip? Horizontal, perpendicular to the axis of rotation. Which means I'm going to have to use two integrals, because from y equals 0 to y equals 2, your horizontal strip has a right boundary of y equals x squared and a left boundary of x equals 0. And from y equals 2 to y equals 4, my horizontal strip has a right boundary of y equals x squared and a left boundary of y equals x plus 2. And when the boundaries of your strip change, you have to use a new interval to do it. There's no other choice. It's terrible. But it's the only thing we've got. Oh, I should also say, your teacher should not say the words shell method, or at least they shouldn't teach the shell method. It's not part of the syllabus in this class. But if they decide to, let me know and we'll talk about it. Again, it's usually not a method, the volume calculation we talk about in 17B, but if they decide they're going to do it, we can certainly cover it. So here, let's look at the top part first. The bottom. Let's look at the bottom part first. So the bottom part, I'm actually going to just get to use the disk method, right? If I'm looking at this bottom thing here, I'm just rotating this strip, which is flush with my axis of rotation, around the y-axis. I'm just getting a nice disk. Or if you want to think of it, I'm getting a washer whose inner radius is 0. So for the bottom, the volume of my washer is pi times the big radius squared minus pi times the little radius squared, just to kind of do that thing once, right? The little radius here would be 0 times dy. So really that's going to go away. We don't need you. And then my large radius is, what is my large radius? Or my only radius, I should say, for this bottom part. Yeah, so like he'll just say it if we be quiet. I mean, it's true, I will. But it's this function over here. So let me ask you all. Am I going to put x squared in there? No, right? I have to put something with y's in it. So instead of y equals x squared, I should be putting x equal to what? Right. And it is the positive square root of y because we are on the right side. If we happen to have this other side over here on the left, it would actually be the negative square root of y because over here on the left, x is negative. And when you square root, you get x equal plus or minus root y, but it's the positive part here. So for the bottom here, our volume for the bottom is going to be the integral pi times the integral of the square root of y squared, which feels silly to write. We should just write y. And that's the square root of y squared. And we're going as low as y equals 0 to as high as y equals 2. That's the volume of my bottom part, which we could totally calculate. That's easy to calculate. I think it's 2. And let's look at the volume of the top. Oh yeah, if you need to go to your test, definitely go to your test. Like you should leave early if you need to go to your test. You don't have to, but you should. So for the volume of the top part, well, first of all, our washer, the top. Well, so now our washer has an outer radius of still the square root of y minus an inner radius of this closer function to the axis of rotation. But that closer function, instead of being y equals x plus 2, it's going to be x equals y minus 2. I like to draw these pictures. All right, y x equals y minus 2 dy. So then the total volume of this top part is going to be the integral from a low value of 2 to a high value of y equals 4 pi times the square root of y squared minus y minus 2 squared dy. And then the total volume, we would add these two things together. Cool. So disk method, washer method, not that terrible. But it really helps if you draw the region, I think. Like honestly, I can't really do these problems without drawing the region. That is how I do them. That's how I've always been taught. That's how most people teach how to do them, is by drawing the region. Time is it? It's 2:54. Okay. Has everyone's class covered volume so far? Okay. Yes. So just because we can finish this easily, this is going to be pi times y squared over 2 evaluated from 0 to 2, which is just going to be pi times 4 over 2. And this one here, if we multiply it out, it's a little bit grosser, but you get, let's see, y minus, that's going to be y squared minus 4y plus 4. Yes, that's a 4. And my 4s are terrible. I'm sorry. Just, yeah. And then I would probably simplify this a little bit and write it as pi times the integral from 2 to 4 of negative y squared minus 4y, plus 4y plus y is plus 5y and minus 4. And then integrate it. And I would end up getting something not wonderful. I'm going to get negative y cubed over 3 plus 5y squared over 2 minus 4y. This is why we don't usually do this, because it ends up being terrible. But you end up getting something. You get pi times, plugging in 4, we get negative 64 thirds plus 16 divided by 2 is 8 times 5 is 40. Minus 4 times 4 is 16. Minus, when you plug in 2, you get negative 8 thirds. 4, 2, 10. 4 times 2 is 8. Whatever that is. And then you would add that to 2 pi, and that would be your answer. Yeah. It doesn't come out nice. It's too bad. Oh well. Anyway. Oh, so the other thing I was going to ask you all is, has anyone talked about volumes? I'm just going to show you this picture because I don't really like to draw it, so I'm not good at drawing it. Has anyone shown you volumes like this? where you're given the base of a solid being some sort of shape, and then the cross sections are like squares or triangles or semicircles. And raise your hand if the answer is yes, or tell me on Zoom if the answer is yes. Cool. They're terrible. I hate doing them. They're just, I mean, they're fine, but like they're just. So okay, cool. If that kind of thing comes up, let me know. We will talk about it. So in the last 3-ish minutes here, any questions, comments, concerns? It could be a question about the test you're about to take that I know nothing about, other than I can say things if you want me to, but I know we only have 3 minutes, so I have no idea how many questions. But I would, oh no, I was gonna say, I was something stupid. I would expect it to be like the practice exam he gave you, but he doesn't give practice exams. Yeah. What's that? Lee doesn't. Lee's tested today, right? Yeah. Lee vehemently does not give practice exams. So yeah. Which is why the practice exam I wrote tried to be more geared towards his class, because they are the ones that needed it. Yeah. I don't know how long it'll be. Usually I've seen from his exams in the past, they don't seem like they are super duper long. Like I feel like maybe the questions might be hard, but usually the exam length is actually, in my opinion, being kind of on the short side. So I would say usual exam advice, don't get stuck. If you get stuck, move on to something else. Look at the test before you really get into it and kind of see if some questions are worth more points than others. Don't waste your time on a 2-point question when there's a 20-point question. And most of all, read the questions carefully. I know there aren't any volumes on this one, but if there was a question like set up the integral, but don't evaluate, don't spend your time evaluating. It's worth nothing. And do show your work, because people usually are trying to award partial credit. So the more work you show, the better chance you have of getting partial credit. Yes. Yeah, good point. So it is certainly true. Oh yeah, I'll say one more. I'll say 2 more things. So certainly the integral from 3 to 3 of any function is equal to 0. And if you see something like the integral from -4 to 4 of x over x to the 6th plus x squared plus 9, don't try to integrate. If you see something that looks gross, that's your hint. That's your hint that this integral is equal to what? Right, because the function is right. Now, I will say, in my opinion, you have to show the function is odd. It's not that terrible, so you have to show. So I would say let f of x equal the function. And then you look at f of -x, which is -x over -x to the 6th plus -x squared plus 9. Simplify, you get -x over x to the 6th plus x squared plus 9. And then you can pull out the -1 and say that's negative x over x to the 6th plus x squared plus 9, which is equal to negative f of x. And that is what you have to show a function is odd. The f of -x is equal to negative f of x. But if you see something that looks super weird like that, or something with like a sine or a tangent, like where it's just like, there's no way you have any idea how to integrate it. It doesn't look like your usual stuff. And you notice that those are opposite numbers of each other, it's almost for sure going to be that it's an odd function. Your interval is equal to 0. All right, it's 3 o'clock. You should stop talking. Good luck on your test. I hope it goes well. We'll see you all on Friday.